So today we're covering pattern matching case expressions right off the bat. Then we'll go into applying that to lists, redefining lists, and then showing you how to use Scala's built-in lists. They're just subtly different. And then we'll define our first interpreter. I guess Sriram probably did one during the week with you guys, but we'll do another on sets on that grammar we were playing with last week. Otherwise, let's just jump into it. So kind of what Sriram should have covered during the week is how pattern matching case expressions work. So this is going to be kind of our default way of doing branching going forward. So probably not a whole lot of if then else anymore. It'll pop up from time to time, but otherwise we're going to pretty much be using case expressions. Why? Why do we like case expressions? For starters, it kind of forces us to get into this functional mindset. We're not dealing with statements anymore. Case expressions are expressions. And they're going to make your functions total. Hopefully, Sriram talked about that a little bit. Total functions means that every input you give has an output. That's not always quite the case in a kind of statement imperative land. You could have a function that kind of exits out or throws errors or does some other weird stuff. So here we're dealing with these total functions. They're always going to have an output, which is a really desirable property when you're writing programs. We'll get more into that later in the coming weeks. But let's take just a quick look at this first example. What output are we getting? Obviously, you guys can run the cell and find out pretty fast. But I'm more concerned with why. Why are we getting an output here? And which one do we get? So somebody walk through this first example with me. Explain to me what's going on here. Anybody can take it.
Well, I guess it's taking the value x and comparing it to each of the cases. So is it 1? It's not. So it moves on to the next case. It's not 2, it's not 3, and then it falls to the last case, and it'll just print the number x, which is
right on. So it'll print something like, I guess it'll just print 10, right? Yeah, because S is a format specifier, I guess, I think. Yeah, so it'll just print out 10. So the idea here in this example is that it's not matching any of these cases. So it's going to always go to this default, which we will typically represent with an underscore. We'll get to a case where you don't use an underscore here in a second. But that's the idea. We don't hit any of these other cases. So we go down to the default case. Any questions about that? Should be a fairly straightforward example. This is your else case if you're thinking about this as an if then else statement, right? So you have if 1, print x equals 1. If 2, print x equals 2. If 3, if else for all those. And then you finally get to the final else statement. There's no qualifier on it. It's just for all else cases, do this print. So it should print 10. Let me know if it doesn't. I'd be curious why. But it should print 10. So questions about that?
This is essentially kind of a switch statement in C or C++, right?
It is identical to a switch statement, right on. The only difference being that a switch statement's allowed to execute, well, I guess cases are too. Cases are allowed to contain statements still. We call them expressions, but expressions in this situation are kind of allowed to contain statements. Again, that's kind of getting into nitty-gritty distinctions that aren't going to matter a whole lot. But right on, this is a switch statement in all but a few very specific ways. So good question, or a good clarification, Dylan. Thanks for that. Actually, they're a little bit more powerful even. We'll get to that in a minute. So any other questions on this example? Super straightforward. Interrupt me if not. So sweet. So I just got a message in chat. Aaron, I saw your message. Sweet. Yeah, we're not taking attendance, I don't think, so you should be all good. Okay, so now on to number 2. So here we're going to kind of look at 2 of them. So first off, I want to just look at this first code listing, and then we'll look at the second in a second. Somebody walk me through this one, just like we did the last. What's going on here?
This one is really similar to the last one, except it's just saying, like, for a case, like, if x is greater than 5, it will print x is greater, like the x value is greater than 5. Same thing for if it's greater than 1, and then if it's less than both of those things, then it would just print the x value, but it would stop at the first condition because it's already met the requirements.
Right, so it's going to print 10 is greater than 5, right? This is to show off basically what we call a guard. So these if statements that are inside the case statement or the case expression are called guards. They allow you to give a Boolean formula. So here, something that, give it a Boolean, and it'll evaluate that. So that's the big takeaway here. You can also use bools to kind of further specify your cases. Now, what happens if, say, this is 0? What prints out?
Should just print just 0.
Right, it's going to go all the way down to this last case.
Hey, Jack, what's up with the underscores right after the case? Isn't that what you said was the else? So why are we using that before the ifs?
Yeah, so it's not quite just the else. So that's the interesting part. And actually, that's a good leading question for this second listing. So ask your question again if it's not clear after this part. So now looking at both together, can you guys see that okay when I'm zoomed out? Little pixelated maybe? What's going on here? What's different in this situation? One big thing.
The only difference here I feel like is that it's instead of like matching to an unused variable, which is just like the underscore, it's matching to a variable y.
Right on. So here, instead of having an unused variable, we match to y. So we give the variable a name. Now, does this give us different behavior, or does it act the same?
When you run it, it acts the same.
It acts the same, right? The other thing I guess that we do different here is we also use y in this part. So it's binding whatever variable we're talking about to y, right? Now, I lost track of who asked that last question. Why do we use an underscore? Isn't that like our else case? Well, it sort of is our else case. It's not quite. What that's doing is it's saying case match on this thing. So here it says case match on y, where y is any value. And then if x is greater than 5, we'll continue on with that branch. What's happening in the first cell is it says if, we match this underscore value, which is the wild card. It says if you match anything, and if x is greater than 5, then we'll continue on. So it's not quite always an else statement. In the first example, it acts like an else statement, but it's different, right? So it's just matching on anything, the wild card. So I'll write this down here. Underscore is the wild card. And what that means is it matches everything. Great set of questions there, guys. Questions about this example, or I guess these two taken together? Or any thoughts or observations? If somebody thinks they see something neat, go ahead and say so too.
So could we get rid of the y and if and just say case x is greater than 5, arrow, print that, and would that work?
So almost, right? So let's take a closer look. What's going on here if I do that? So if I just used, say, X here, what happens?
It'll say like val y not found or something.
Yeah,
Right?
Y undefined probably, right? Or not found, something like that. So you could almost do that if you swap the Y out in there as well. Or maybe you have Y defined somewhere else and you want that behavior. But yes, you could change the names, you could make it X, you could do anything you want. Really there, just as long, it's kind of about a program behavior thing. Is this the behavior I want from the program? Here we're just putting Y there to kind of show you can bind Y, right? So that's all we're doing here. We could also change this X to a Y. That would work just as well. I believe. I don't think there'd be a problem with that. So to answer your question, yes, you could swap that out for the wild card, as we saw in the previous example. You could put X there. It would rebind X, right? So it would make X within this clause not this X anymore. It would be a different X, right? For terms of like referring to variables. So if X was a different value, you'd get some interesting behavior there. But otherwise, for instance, if it said Y here and then you had X here, it would make X equal to that Y, whatever that Y is. So that is what's going on there. Any other questions about this example? Good questions, guys. You guys are on fire this morning. Cool. Let's move on to the third one. Keeping a good pace today. So I want us to let's start with just looking at this first code listing, but these are all kind of part of the same example. So start with this guy. What's going on here? This looks a lot different than the others.
Is it just like, is that the case if y is 10, 20, or 30?
Right on. So, I mean, and you can read that from the text, right? It says that. But what's going on with this y here? What's going on there? We haven't seen that before.
Would it be just the sort of syntax to compare like y to 10, then 20, then 30, or whichever one returns true first?
So yes, I think you're hitting it right. What's happening here is we're saying bind whatever we're matching to y. So now we still have this variable y that we can play with. It's getting named. And then it's matching on 10, 20, or 30, right? So we're doing a little bit extra. We're saying this is 10, 20, or 30 and bind it to y if it hits any of those cases. And that's why we're allowed to use y inside here. Okay. So this binds y basically to that value. And then a typical kind of undefined or otherwise default case down there.
Is there some advantage to using this y because you can just change it to x in both spots and it works?
Yeah, so for these examples, they're a little degenerate just to show off how the syntax works. There are situations all the time when you'll want to use kind of a y at notation. It comes in more when you're playing around with actual constructors for the numbers. It doesn't make a whole lot of sense. This is the kind of application where you would use it with numbers. But there's a better use case that we'll see probably, I think, later today. We should see it. Otherwise, I'll manufacture an example in a little bit to kind of show
Real quick,
yeah.
I'm just kind of confused, like, because we're using this at to kind of bind it there. So then what is it doing when we do like the tail recursion at sign above like a tail recursive function?
Yeah, so that is an annotation, and that will always occur before a function. There are different at signs.
Okay.
And in just about any other language, you wouldn't see syntax overloading like that, but they just do in Scala for some reason. this at actually that we're seeing here is pretty typical in any functional language you'll come across, or quite a few of them. So I believe this use is inspired by Haskell, where you use the same binding procedure when you need to bind the variable but also match. So any other questions? Good question, Jack. I like that one. Okay, let's move on to the next one. So similar situation here, or I guess I should ask, what output do we get here? We get the first line because x matches to 10. But now let's look at the next one. Here we have x is 10. What happens here? What output are we getting?
Just 10.
Just 10, right? So while we're still binding y here, and x does match on just the y part, it's not matching on this piece, and we need it to do on both. So that's really important. Just keep that in mind. It'll skip to the next case because it doesn't meet all the requirements in the case piece. So next part, what happens here?
Are we just using like our blank case as like a blank, like it could be any number? Is that what's happening? Is that
That's exactly what's happening here. So here we have val x equals 10. It's going to spit out this first line. So y is either 1, 2, or whatever. It has the wild card, so it'll match on anything. It says 1 or 2 or wild card, so it matches there. So you can also put wild cards inside these. This is doing matching. That's the big takeaway. The inside of the parens. It does pattern matching, and then it binds whatever was matched to y. So you can do a match, but then also use the entire expression if you want. So you can keep around the variable. This lets us do something like collapse. Like I could have a case for 1, a case for 2, and a case for wildcard, but they all do the same thing. So we want these all to really be defined as succinctly as possible. So we'll use a single case with this syntax, just because it saves us space. It's purely kind of a syntactic sugar is what we call it, to make our lives a little bit easier, make our code more readable kind of thing. So all three of these examples more or less do the same thing. They do it on different numbers. They do it a little differently, but they're essentially just matching kind of the inner structure of what y is. This will get really, like I said before, really useful later. So questions about this example? Sweet. Like I said, super simple relatively. There's some weird nuances here as we can see. But it's all to make our lives easier in the long run. So keep that in mind. If you're ever writing a program in a functional style and it's like, I keep writing the same line over and over again, there's probably a shortcut to make your life a lot easier. That's the rule in functional programming. If it seems tedious, there's probably a better way of writing it. Actually, I'm going to write that down because that's like, if anything sticks with you during this class, I want it to be that. So okay, so that's like one of the big rules this semester. Remember that. I'll say it a bunch of times. If it seems tedious or redundant, it probably is. Sweet. So let's move on. If you guys have other questions, stop me. But let's move on to lists. So this will kind of show where this case matching thing is a little bit more useful. So we're defining lists in the my list version. So just pay attention to the top part for now. And this should answer, Dylan, your question a little bit on how to go between the two. So if I have a grammar here, I'm saying I have this type called my list, right? So I'm creating a user-defined data type. and this is the grammar for it. So I have my nil, so the empty list is nil, right? And I have my cons, which is just the list constructor. So you give it an integer and another list, and that creates a list, right? So these are both kind of list constructors, as we say. The nice thing about constructors is that we can match on them, which is what you see directly below. But first, how do we define this in Scala? How do we go from one to the other? So for my nil, because it doesn't take any arguments, we'll call it a case object, okay? And we'll say it extends num list here. Always remember to, if you're defining a new type, call it a sealed trait num list, like so. And that kind of just tells the compiler, hey, I've got a list. It's a new type. This is what it's defined as, and you define the cases for it. So case object my nil, and then you have a case class. Classes are allowed to have arguments given to it, or other stuff inside it you can think of as well, other structures inside. And here we have cons. It takes the first element, an integer, and the rest of the list, num list. Okay. It extends num list, so it's a constructor for num list. Questions on how we got from one to the other, Dylan? This is your shot. We can always do more examples later too, but it's unclear how I went from one to the other.
Wait, what did you say? Did you say it always needs an empty constructor?
So
or object?
Yeah, technically no, it doesn't. Because you could imagine my nil, instead of having the empty list as kind of your base case for these, you could have the singleton list be the base case, which would define a little bit of a different type, right? The type would be the type of lists of at least size 1, right? But that would be a case class, right? So I could define, say, case class singleton, and it could just take some element x of type int, and I could say that extends num list. So you don't necessarily always need an object. You often will, almost always you will, but that's not always the case. It just depends on your grammar. Does your grammar refer to other types or not? This is the case where it does. We'd call this kind of a terminal constructor. It doesn't call on num list again within the constructor. It just kind of calls some other type. So it kind of terminates the num list, you could think of. Not quite a great analogy, but it works here. So that's how we go from one to the other. Now, how the heck do we use my list? So actually, I'll use my other Zoom here. So when we look at my length, we're defining the length function. I just want to know the length of my list. We're allowed to match on those cases we just defined. So my nil and my cons, it's exactly what we're doing. We're just matching on them. So we give a list to the argument, or a list as an argument to my length. We immediately match on it. That's what's going on right here. And that has a couple cases, right? So we have the case for my nil and my cons. My cons has a few arguments inside it, whereas my nil does not. And we need to say, okay, well, what do we do here in order to count the list? So I'll give you guys a second to think through that one. Figure out what should go in the question marks. You know, how do we fill these holes? Here and here. I'll give you like a minute or two to think that one over. Hint, it should involve a recursive call. Okay, anyone have some thoughts for me?
Yeah. Would the recursive call be in the second case, the mycons would be like 1 plus my length list, but without the first element, and then my null would just be 0.
Okay, so you're saying, right, something like 1 plus my length.
I don't really know how to take off the first element easily, but
And then, yeah, so you have to give it another list. How do you take off the first element in the list?
Just give it rest of list.
Just give it rest of list. So this is where the case matching, pattern matching really shines. Is that because you've matched on it, it is already giving you the rest of the list. You don't need to do anything else because that first element's getting appended to the front. Say you wanted to pass in the whole list. I could rewrite, which would be a non-terminating function. That'd be a problem. We don't want to do that. But you could also give it mycons first element rest of list, right? Or what you could do, this is where the at comes in handy. You could do y at and then the mycon stuff. But we don't want to do that because that wouldn't terminate. So just to kind of show off to you guys when you might use that, that's exactly when. So yeah, so just give it rest of list. So what else goes in the other missing section? What are we putting there?
Wait, so is it 1 plus the my length rest of list, or is it first element?
It's going to be rest of list. We're going to forget about first element.
Oh, just like completely? We're just doing the
Yep.
1 plus. Okay.
So you could put an underscore there as well, right? Because we don't care about it. So I could have written, for instance, mycons and then put an empty there and then put rest of list. Like so. That would have been just as good.
Oh, I meant for the solution, like the 1 plus my length.
Oh, why you don't use first element?
Yeah, what's that one?
Yeah, the one's just the number one, right? Because we're counting the number of elements in the list. So we can think of, we're pulling off first element, throwing it away, right? That's why you could put the underscore there. And then on this side, we're kind of replacing it with a 1 and adding it to the result of the recursive call, which is counting the rest of the list. I'll show you an execution of this when we're done and show you how it actually works. I think that'll be a good little example. So now what do I put on the other side of my nil? What goes there?
Just
0.
Just 0. Why does 0 go there?
It's the base case.
Well, that's great. What does that mean?
Like it's at the end of our thing. We don't need to add any more. Like there's nothing left in the list.
Okay. What if I pass an empty list to the function?
You should return 0.
Right on, because it's an empty list. Length is 0. So there's a couple ways you could look at that. It's the base case. When we're counting something, the base case is almost always going to be 0, right? Maybe not always, but most of the time. And then also the empty list is 0, so that makes sense, right? So now let's just do a practice execution on this function. So let's say I give it a list, and this will be our list. So I have a mycons in the front with 3 and another mycons with 2. And my nil there. What happens when we execute this on my length? What case do we match on at the beginning?
first you'd go into the second case, it starts with my const.
Right, right. And we match on that. So, and it gives us 1 plus my length. And inside my length, we have rest of list. What's rest of list in this case?
My cons to my nil.
Right on. So my cons 2 and my nil. Okay. Now what happens when we keep executing and reducing this? So we have 1 plus, we can't reduce that. But what does my length, my cons 2, and my nil give?
It just returns 0.
Does it?
It should match on my cons and then do 1 plus my length of my nil.
Okay, so 1 plus my length of my nil. Okay, and whoever said that before, what does this give back?
Now it returns 0.
Now it returns 0, right on. So now we have 1 plus 1 plus 0. We do that handy old arithmetic thing that we learned in elementary school, and we get 2. That's the length of the list, right? So this is how this is going to execute, right? We like it. It works. When in doubt, always just do an execution by hand and make sure it's doing what you expect it to. That's always a handy trick to do.
What is it assigned to, like, first element in all of the levels past
Yeah.
the
So
first?
here, so in the first element is this guy. In the second, first element is going to be, let's see, 2. And then down here, it matches on a different case. So there's no first element, right? And then the rest of list is, I'll use a different color. Rest of list is this. And then here, rest of list is just my nil. And then in this last case, there is no rest of list because it matches on a different case. Does that answer your question?
Yes, but I don't quite, like, I guess that's just because of case matching, right? I'm kind of confused on how I knew the first element of the list was still the, oh, I guess because it looks, okay, never mind, I get it.
Yeah, it sees my cons at the front, right? And then it just knows, oh, whatever comes after this is going to be a first element and then a comma and then the rest, a rest of list, which is a list, right? So it's just matching on the, literally kind of on the strings and expanding it out and saying, okay, where are my parentheses? Where are my commas? That's telling me what everything is. So it's super like on the rails the entire time. There's no guesswork. Pattern matching isn't doing anything like a neural net does, because neural nets kind of do pattern matching, right? But it's not the same kind. This is very on the rails, very syntactic. You know what you're getting every time. It's not doing anything magical, just math. So any questions about this example? Cool. So now I'm going to confuse y'all with syntax. So we never will use my list again, I hope. I don't think we should. Plus the syntax is just too big. It takes too much space to write this stuff. So instead, we're going to have a list, and for the rest of the semester, define lists in this way. And this is the grammar for it. So we have the empty list. We'll still call it nil. And then we also have the cons case again, the constructor, except that this time cons is going to be an operator. So cons will always come in between an integer and another list. Or rather, actually, if I'm being more precise, it should come in between, I guess it goofed up when I was writing this morning, should come in between an alpha and another list. What the heck is alpha here? There's a P word that you guys probably learned once upon a time.
Is it predecessor?
No, not quite. This would have been in another class you probably would have learned this term. So we say this alpha is a, well, it makes a list polymorphic the alpha is what we call a type variable. And this basically says, whatever alpha is, just give me a type and I'll make that alpha become that type. So in this situation down here, we're giving it an integer. So we're specializing this to lists of integers. So I could, because iPads are cool and you can copy and paste stuff, when I specialize this, I can imagine I'm getting rid of this alpha everywhere it occurs and replacing it with int. So I put an int here. I put an int here. And I put int here. Now this should look awfully darn familiar to this definition up there. Awfully familiar, right? Very similar. It's a little different, but it's structurally the same, right? So just know that this is how we're going to write, you know, because you might want, for instance, a list of booleans or a list of lists, maybe. This is how you do that. We haven't covered this yet. I'm just giving you a little bit of a taste now, because the syntax is in this function. So just to give you a little taste of what's to come, that's what we're doing here. So now that I've probably confused most of you, how do we fill out this length function? How is it different?
So are you saying that the alpha character, the polymorphic thing, kind of matches to a type? You just kind of don't have to specify the type when you use it?
Sorta, yeah. You do have to specify the type when you need it to be a certain type, but it's saying I can have a list of anything, right? And this is where that anything occurs in the constructors.
Okay.
More, like I said, more on that later. It's not really important for this example. So just, like I said, just a taste. I don't want to get into it too much today because it'd be a diversion. So yeah, so let's just focus for now on how to fill out this length function. How do we do this? This shouldn't be too difficult of an exercise.
Is your case nil is 0 again?
It is indeed. So
That's
now,
all I got. I don't know about that.
and then how about the next case?
Would you use the same exact line that we used before?
Exactly, just about. So here we're going to have 1 plus and then the recursive call. And rest of list. So same function, operates the same way. We're basically just changing the name of the recursive call, right, which we need to do. So that's how we do that with the built-in lists. Not really sure why we do that today, but we're doing it today. So you'll see lists use this double colon instead of writing out the constructor. It just makes things look nicer. So if we want to, let's just do an execution on this again. So the same list as we did up here is going to be written a little bit differently this time. So this time we're going to have 3 cons, 2 cons, nil. Like so. So that's how we would write the same list. So now how do we execute this? So length of this guy is equal to, and then we already know the first case, it's matching on the second case here. And so we have 1 plus length of 2 cons nil. And then we have 1 plus 1 plus length of nil, which of course is 1 plus 1 plus 0, and that equals 2. So same function, same example. As you can see, this other syntax is way easier to work with. Takes up a lot less space. It's a lot less messy. So we prefer that. Any questions or takeaways, thoughts? Great, sweet. So now the next example, we're going to write our first interpreter. We'll write a lot of interpreters in this class. As you guys can read in the instructions, I'd recommend doing it real quick. We're going to write an interpreter for the language of sets we created last week. So you can see here, we've already written a case expression for all those constructors we defined last week. Now, and if you need a refresher for what that class looks like or what that type looks like, it's right above the exercise. What we want to do is map this onto the built-in sets that Scala has. So there are all these set functions. There's like set.plus, set.intersect, set.union, set.diff. How do we take our class and map it onto the functionality we want from set?
So for case empty, could you just put an empty set of curly braces?
Right. I'm not sure what the syntax is for it. Is it just curly braces?
Yeah, I'm not positive on that either, actually.
Yeah, because curly braces are usually special. Let me actually open up the documentation. I should have done this before.
Doesn't nil represent an empty set in Scala, or would it just be curly braces?
Let me just double check. I don't want to tell you guys wrong. Sets. Let's see. So the way we're going to write it, and I'm not sure if this should be correct. We're actually just going to write set, oh, wrong color, with nothing inside it, like so. I believe is how you write that. Somebody check me on that. If you run that program, it should freak out if that's not the right way to write that. Did that work?
Chat says yeah.
Okay, cool. I like it. Oh, the first test case shows that's, oh, perfect. I guess I could have just read the next cell. Good job. Good work, guys. You beat the TA today. So now how about the cons case? What do we put there?
Is it just set s comma n?
Set s comma n. Is that right? So we're expecting s or set to take a list of numbers, right? Or a set of numbers. What is n?
Just an integer.
Or sorry, what is s? Not n. N is a number.
Is it a set?
That's a set, but that's a my set, right? And set doesn't take my set, it takes int. So how do we turn my set into an integer or a set of integers?
Right, set int?
Not quite. So I'm going to cheat for you guys and just tell you, because this is kind of the idea of the interpreter. So we're almost right with writing. We do want set and n inside a set. So that's right on. We do want that. But instead, or actually, we're not actually going to do it that way. What we're going to do is write eval s. That's going to give us a set of integers. Okay, so we're making a recursive call to turn s into a Scala set. That's what we need. We can't give it a my set. And then we add to it n. If you guys look at the plus function from set, which is just above the cell you should be looking at, it takes a set of integers and an int and adds that and gives you a new set of integers. So this is like the cons case is just in the opposite order. Any confusion there? Big takeaway is we're making a recursive call to eval. We're using eval to define eval. So any ideas on how we do intersection, union, and subtraction?
Would intersection be eval s times n?
Not it might work. I'm not sure if times is defined, but try using the functions that are in the cell above the cell we're looking at.
Dot intersect instead of times.
Yeah, so we're gonna do intersect. And it takes two arguments, as we can see above. What are those two arguments gonna be?
Isn't it just S1 and S2 because they're already sets?
What kind of sets are they?
I don't know where would it say that.
Yeah, so intersection, remember, is defined up in the cell above. So it takes a my set and a my set. So S1 and S2 are actually my sets, not
I think it's
eval.
eval of each of them.
Yeah, so we need to evaluate them first. So we're gonna do eval S1 and eval S2. So you're almost right. We just need to turn those into Scala sets first using our eval function. Now, how about union?
Wouldn't it just be the same thing? But
Same, yes, same thing, but just with the union call.
And same for subtraction too.
And same for subtraction too. Right on, guys. So, and if we had tried it just plugging S1 and S2, you would have gotten a type error. So this is where the type checker is going to actually help us a lot with these kind of errors. So we do subtraction eval S1 and eval S2. So like so. And that's our first interpreter. If you gave it a my set, it would turn it into a Scala set or interpret it as a Scala set. So we can think about as interpreters as taking one type and evaluating it into another, or converting it into another, interpreting, evaluating. All these things work. So what we'll do later is represent, we'll start writing programming languages as these sealed traits. And what eval will do is take that language and convert it into some result, some kind of computational result. So that might be a number with arithmetic, say, to find the language of arithmetic. Have like plus, minus, divide, stuff like that, and have numbers in there as well. And then my evaluator could turn an arithmetic expression into just a number, evaluate it, right? This is what we'll be doing basically the rest of the semester is building these evaluators, making them more and more complex as we go, until you guys just kind of know how to write languages from the bottom up using these kind of methods. So any questions about this example or anything we went over today, anything you guys want to cover? We got about 5 more minutes. That being said, if you don't have questions, you're free to go. That's all we needed to cover today. So we blazed through it.
I actually had a quick question regarding the homework. I finished it yesterday, but just like looking at the stuff from today, I kind of think I may have done like the one of the parts, like the 3A